Hi everyone, it's Mr. Baker here. Today we're going to be looking at Hooke's law. So Hooke's law is all to do with how much a spring will stretch depending on how much weight you will put on it. And so we'll be looking at extension and how that's linked in with the weight and how that's linked in with something called the spring constant, basically how stretchy or how stiff a spring is. So this is what Hooke's law is. Hooke's law states that the extension of a spring is directly proportional to the force applied, provided its limit of proportionality is not exceeded. Okay, so that's Hooke's law. I thought we'd get that out of the way, and then we'll look at what actually all of that means. Okay, so what we've got here is we've got a spring, and we've got like a force meter here, which we can see on here. We've got where the spring is starting from. And then as I add some force, you can see this green arrow showing us how much the spring is extended, how much it's got bigger, and this reddy orangey arrow here is showing you how much force I've put in. So you can see as I put more force in, the spring has got bigger, it's extended. Okay, and what you should see is if I put it to there, so I've got a force, and we know that a force is given by this. We use this arrow to represent the force, and this force is like a scale drawing of how much the force is. In this case, it's actually 49 newtons. Let's get that to exactly 50 newtons. So that's 50 newtons, and I've got this distance here, which is the extension of the spring. Now, if I double that and make that 100, so I've doubled the force. You should be able to see that I've doubled the extension, and this is basically what Hooke's law says. When you double the force that you put on a spring, then you double the extension. So as we've just said, when something's directly proportional, if you increase something, the other thing will increase, and it'll be a certain amount, it'll be a steady amount, and that's basically what we've got here. So as I double the force, I've doubled the extension, and that's basically what Hooke's law will say. And depending on this thing here, the spring constant, will depend on how much the spring will stretch. So let me show you another example. Let's go back to 0. So we had an extension there of that big, so try and remember how big that was. If I increase the spring constant, so by increasing the spring constant, what I'm doing is I'm making it harder. It's a stiffer spring. Let's make that exactly 500, because why not? Okay, so now if I try and stretch the spring with the same force that I had before, look, the extension isn't as much. Okay, so this is what Hooke's law says. Hooke's law says that the force is directly proportional to the extension, and that will depend on this thing here, the spring constant. The bigger the spring constant, the harder it will be to extend the spring. And that's basically all Hooke's law says. What Hooke's law does go on to say is that this will happen up to a certain point, the limit of proportionality, and then after this point, when you stretch the string past this point, it won't go back to its original length. Okay, and we'll look at that in a little bit more detail later on. Okay, so we've said that the force is directly proportional to the extension, and so we get this equation here. Force equals the spring constant times the extension. Force is the symbol F, and we measure that in newtons. The spring constant, we normally give the symbol K, and that's got the units of newtons per meter. And then extension is just E, little e for extension, and that's measured in meters. And as I've said before in the last bit there, the spring constant is basically the stiffness of the spring. It's the force per unit extension needed to stretch it. Okay, so we've said that the force is directly proportional to the extension, and that will depend on the spring constant, depending on how stiff that spring is. And we'd get a graph like this. So as I increase the force, then the extension will go up as well. And you can see that it's a straight line that goes through the origin. And that's what we say when something's directly proportional, we get a straight line through the origin. Force is directly proportional to extension. For this portion, up till here, and this point here we call the limit of proportionality, or the elastic limit. And then as you can see, as we stretch it past that point, it does this. And actually what would happen is that if I let go with the force, it would go back, and it would have some extension, so it would actually follow this sort of line back, and the spring wouldn't go back to its original length anymore. It would have a certain extension, depending on how far I'd pulled it. Okay, so there's something else we can talk about with Hooke's law, and that's how much energy. We know that when we stretch a spring, it's got some elastic energy that's stored in that spring, and we know that energy transferred is the same thing as work done. We also know that work done is force times distance. So if a spring is pulled with a force and extends a specific distance, the energy must be transferred, and it's stored as elastic potential energy. So we can write that as elastic potential energy equals 0.5 half times the spring constant times the extension squared. Okay, so it's an equation that you've got to be able to use. So the strain energy equals half times K, which is the spring constant, times E squared. E is the extension. Okay, so there's so we've got a couple of equations that we've got to be able to use in this topic. And what we'll do is we'll just go through a few examples. Okay, so let's think of an example here. So we've got a catapult. What we're going to do with this catapult in this example is we're going to stretch it and then just fire something directly upwards. It's going to be propelled vertically. The elastic in the catapult is extended 0.2 meters, so it's got an extension of 0.2, and the spring, in this case the elastic, has got a spring constant of 100 newtons per meter. So if the object is 0.02 kilograms, and given that gravity is 10 meters per second, how high will the object go? Right, so what I want you to do is see if you can do this. Have a look back at the equations we've looked at so far. What equations do you think we would need to use? What information have we got here? So try and write down what we've got, all the different information, and then see how far you can get, and I'll explain what the answer is. Okay, so what we can do is we can work out how much elastic potential energy there will be in this catapult. So the strain energy here equals half times the spring constant times the extension squared, half KE squared. So that equals half times 100. So our spring constant was 100 newton per meter. Our extension was 0.2. And so if we do half times 100 times 0.2 squared, that equals 2 joules. So the amount of energy that we've got stored in our stretched catapult is 2 joules. So that's the first thing. So we've got to somehow then use this information to find how high it will go. So we've got the elastic energy. The other type of energy that might be useful in this question is the gravitational potential energy. And we know an equation for gravitational potential energy, so we know that the stored energy here we could put into transfer the energy into that object, which is 0.02 kilograms, and we could find out how high it would go. Like this. So we know that the equation for gravitational potential energy is the mass times the gravity times the height. So if we say that all of the energy in the catapult is going to go into this object that's being propelled upwards, so there's no energy lost, then we can say that our elastic potential energy, which is 2 joules, is going to equal the gravitational potential energy, and that's going to equal the mass of the object, 0.02 kilograms, times gravity, which is 10, which is there, times the height. So then our height is going to be 2 joules divided by 0.02 times 10. So that means that if we had this catapult and we had an object of 0.02 kilograms, it would be fired 10 meters into the air. Okay, so just work through this, check that you understand how I got to that answer. For this lesson, we have looked at the equation for Hooke's law, looked at how force is linked to the extension and the spring constant. We've seen how that links in with our equation for elastic potential energy, and then we've used that to see how it can be transferred to different energy stores in terms of the gravitational potential energy. So that's what you really need to do. You need to have a look at those equations and then really just practice using those equations. Okay, so that's it for this lesson. Thanks very much. It's been Mr. Baker here, and I'll see you next time. Thanks.